That's where the different graphs we have available here, they will help. For example, let me come here. You might try to compare your NPV. Here, let me make a scatter plot, okay, of my NPV versus, let's say, the project capex or the total cost. So I get a scatter plot of how your NPV is dropping while the project cost increases, okay? You might try to understand how the different variables affect each other by using scatter plots, box plots, trend graphs. You might even try to compare different distributions. So in this case here, let me just clear this out. I might try to compare, for example, the cash flow on year number 3 or year number 4 when I'm supposed to be making a lot of money. Year number 4 with, let's say, year number 3, and see how it changes over time. So how is my cash flow changing over time? How likely is it that on a given month I'll have a negative cash flow? You can start exploring all the outputs of your model and understanding where risk is coming from. I'll even create another chart here where I have all the cash flows together in one given chart, a summary trend chart as we call it. And on this chart, I can see how the cash flow is evolving over time, okay? In red here, we have one possible scenario for the simulation, and the scenario is changing, so all these scenarios are possible. For my cash flows over time, okay? So what is the actual cash flow that was simulated? If you get all the simulation results, you can calculate what's the average for each month, and that's the black line we have here. Around the black line, we have a 50% confidence interval and a 90% confidence interval. So if you look at the numbers, you'll see that right after you make the huge investment on the project, on the plant, $1 million, on the first time step when you're actually making money, it's probably 0, the average. There's a very high likelihood you will need more money. You have a negative cash flow in the first month of operation, and also on the second month of operation. As you can see, 0 here is breached on the first and the second month. The third month, the likelihood of 0 is less than 5%. It's out of the bounds of the graph, which is good. But for the first 2 months, you might need money, and you might need another money, 150, 100. Okay, so it's a very pessimistic piece of news. Then, of course, the cash flow is very positive for a long time, but there, in month number 13, you might have problems again. The cash flow dropped to close to 0, maybe negative. For more capex right now to spend making sure that the project survives, and in the future we need more money. We need to save to survive this point in time. Okay, there's a number of ways you can create graphs and comparisons and try to understand where risk is coming from. Okay, another thing we can do besides modeling distributions per se, in at risk we have fitting capabilities. So imagine you have historical data for your other projects and have historical data to try to guess what distributions represent the data. You can do that with distribution fitting. We're not going to go into this right now, but you can do that, and then you understand, you will learn what distributions represent the data. I'll go real quick here. We're not going to do this in much detail, but distribution fitting lets you transform a data set or a group of a group of variables into a distribution that you can use right away. So for example, here I discovered the name and the equation for each of my risks. So capex project behaves like a risk triangular, infrastructure like a PERT, the other one like a normal, and the other one Pearson, which is more or less like a log normal distribution. It also calculates the correlations for you, and it gives you a report with everything you need to go from a data set into distributions directly into your model. You can also do that with time series. So if you have, like we have here, market data, historical data over time for sales, material costs, product price, and you can see the graph here for sales. The volume of sales has a clear seasonal pattern. Material cost also has a clear seasonal pattern. Maybe product price also has, I don't know. We can use distribution fitting in at risk, or better, time series fitting in at risk, to understand how these variables evolve over time. It also provides you a summary of each variable, how it behaves over time in the past and how it might behave in the future. So I can use that directly into the models. Okay, so using data in at risk, these are only two ways to use data. There are more ways that you can use data directly in your model. Is one possibility. Or you can rely on expert opinion and define your distributions based on the parameters that you learn or received or believe in. Okay. After you set up your model and run, there's a number of other graphs to discuss here: scatter plots, summary trends, even the raw data of the simulation if it's available if you ever need it. Okay. There's one last thing I would like to do here in the last minute, which is, we saw that this project is very risky, right? We saw that there's a very large probability of negative returns, of not paying for the whole project, negative NPV, 20%, which is bad. Let's suppose there's an opportunity to make a contract with our main client, okay? We will sell a certain volume fixed in contract, so no more volatility on volumes, based on the historical average. So the historical average is 40,000. We're gonna make a contract to supply every month 40,000 units. And the price, we're gonna have to give him a discount. Based on the historical average, based on 1624, which is the historical average, we will offer the client a discount in order to fix volumes and fix prices. Of course, the material cost, the cost of materials here, the input cost, is still with us. It's still volatile. There's nothing we can do about that, at least not with this contract. Does this make sense to fix volumes and prices in terms of risk analysis? Well, at first it should make sense. If there is no discount at all, if I'm selling everything at the historical average, we can easily see what happens with the result here. The volatility of the NPV decreases. Therefore, the likelihood of negative NPVs, which is on the left tail, probably will decrease too. Let's see what happens here. So if you sign this contract with your client and with no discount at all, at the average of historical volumes and prices, you'll see that it's still a profitable project, and the likelihood of losing money dropped from 20 to about 6%. So you reduced risk, and here when I say risk, the threat of losing money, you reduced that a lot. Okay, the likelihood of losing more than 0.5 million, which was almost 2%, dropped to almost 0. So it seems like a good idea to sign this contract, but I would guess your client would require a discount to take this risk, right? Because sometimes the cost is the cost in the market is less than that. You're making a long-term commitment. They might require a discount. What is the maximum discount we can provide, we should offer in this contract? That's something we can figure out with GoalSeek, okay? And when you're dealing with risk analysis and with the decisions you make with them, you tend to think about the decision process in a wider way. So what I'm gonna try to do here, just like in Excel's GoalSeek, I'll try to make a given cell, make some statistic of that cell drop to 0. We saw that with the original project, there was a 20% chance that this NPV would be 0, right? I would accept up to 10% chances of negative NPVs as a risk that I'm taking with this project. So I'm going to try to find what's the discount that makes my NPV percentile 10 drop to 0. And at risk will do that for us real quick here. just like Excel's goal seek, the deterministic goal seek, it will test different strategies, different values on that cell. But for each value, it will run a full Monte Carlo simulation to try to figure out the distribution of the NPV, and therefore the likelihood that the NPV is 0. So I finished the first simulation. In a couple of seconds, it should finish the second simulation. It's about 10-15 seconds for each simulation. And once it tries maybe 3 or 4 different values, it will figure out the discount that makes that number, that cell match, the distribution match exactly what we want. So not only we can assess risks, we can also play with the idea of minimums, maximums, threshold values that make the business case make sense, that make the project better from the risk perspective, okay? So that's what we're trying to do here. We go seeking for a threshold value below which my project makes sense, above which it doesn't. In this case, not the project, but the contract, okay? This threshold value, this discount I'm looking for here, it's probably gonna be around 1 or 2%, I guess. So with that level of discount, it makes sense to have this contract. If the discount is higher, if they ask for 10 or 5% discount, then it's better not to sign this contract and take the risks as they are. Otherwise, you would have even a worse situation for your project, okay? You can use goal seek like this to figure out what's the minimum production you need or sales force you need to be profitable. What's the maximum capex you can pay for something and still be profitable? What's the minimum number of units you need, the maximum number of units that fit within your budget, okay? There's a number of ways to explore goal seek within the context of risk analysis. So just to finish here, the last example, it ran the simulation and it figured out that with a 1.21% discount, we do have a likelihood of 10% of going negative. So the project is better right now. Before I had a 20% chance of losing money, now I have a 10% chance of losing money. Actually, let me explore that. I will plot the two charts together so we can see that. The original chart in red and this mitigated chart in blue. So the mitigated version of my project. Before I had 20% odds on the red graph of losing money. Now with this new contract, with this mitigation plan, mitigation strategy, I have only 10%.